Right now, 130 million miles from Earth, something is happening that shouldn't be possible. An object the size of Manhattan is hurtling through our solar system at 210,000 kilometers per hour, spewing glowing metal into space, surrounded by more frozen carbon dioxide than water. And it just survived a direct hit from one of the most powerful plasma storms the sun has thrown at anything this year. And here's the thing that has some scientists quietly concerned. It's behaving exactly like it knows what it's doing. This is 3I Atlas, the third confirmed visitor from another star system. And based on what we've learned in the last 2 weeks, either everything we thought we knew about comets is wrong, or we're watching something far more interesting than a ball of dirty ice. Let me show you what I mean. October 27th, 2025. The comet reaches perihelion, its closest approach to the sun. Russian astronomers at the Space Research Institute are monitoring something unprecedented. One of the most massive coronal mass ejections of the current solar cycle is barreling directly toward 3I Atlas. This isn't just solar wind. This is a wall of superheated plasma, traveling at millions of kilometers per hour, carrying the energy of millions of nuclear bombs. For context, these are the events that can knock out power grids on Earth from 150 million kilometers away. This thing is about to take a direct hit. The question everyone's asking, will it survive? Most comets that get this close to the sun don't fare well. They fragment. They dissolve. They simply cease to exist as coherent objects. And this visitor from interstellar space, already showing behaviors we've never seen before, is about to be stress tested by the most violent environment in our solar system. The data streams in. The plasma cloud strikes. And 3I Atlas doesn't even flinch. Not only does it survive, it maintains its exact predicted trajectory. No deviation, no fragmentation, no change in behavior whatsoever. It's like watching a ship navigate through a hurricane without adjusting course. The Russian team releases their findings. The signal is exceptionally weak, but 3I Atlas remains on its calculated trajectory. That word exceptionally is doing a lot of work there. This object should be screaming in every wavelength after an impact like that. Instead, it's barely whispering. So, what exactly are we dealing with? Let's back up to what happened just days before this solar encounter, because that's where things get really strange. October 15th, the comet passes within 12 miles of Mars. 12 miles. That's closer than most satellites orbit Earth. NASA's HiRISE camera aboard the Mars Reconnaissance Orbiter, one of the most powerful cameras we have in space, captures the closest images ever taken of an interstellar object. Think about what that means. We have photographs of something from another star system, taken from 12 miles away. The resolution should be extraordinary. We should be seeing surface features, jet structures, maybe even composition variations across the nucleus. But there's a problem. NASA hasn't released the images yet. Not because they can't, but because what they show doesn't fit. Those photographs, potentially the most important ever taken of an interstellar object, are locked in internal review, unseen by the public. Researchers who've glimpsed them are tight-lipped, but they keep hinting that the data could reveal new details about the comet's jets and surface. In science, could doesn't mean maybe. It means we already know something's wrong. Could reveal, not might show, could reveal. That phrasing is deliberate. They've seen something. While we wait for those images, let's talk about what we do know. And trust me, what we know is already breaking every rule in the book. August 14th, 2025. The Very Large Telescope in Chile, one of the most sophisticated observatories on Earth, is tracking 3I Atlas when it's still nearly 4 times farther from the Sun than Earth. At this distance, the comet should be a frozen, inert chunk of ice and rock. Nothing should be happening. It's too cold, too far from the sun's heat. But the spectroscopes detect something impossible: glowing nickel vapor. Not just traces. We're talking about a clear, unmistakable signature of nickel in the gaseous state, surrounding the comet like an aura. Rohan Rahatgaonkar and Daryl Seligman, the researchers who made the discovery, are staring at data that doesn't make sense. Nickel has a boiling point of 2,913 degrees Celsius. At the comet's distance from the sun, even the sunlit side should be somewhere around negative 100 degrees Celsius. That's a temperature gap of 3,000 degrees. You don't accidentally bridge that gap. Here's where it gets weirder. There's no iron. Nickel and iron are cosmic twins. They form together, melt together, vaporize together. Every comet, every asteroid, every meteorite we've ever studied that contains nickel also contains iron, usually in similar ratios. It's one of the most reliable patterns in planetary science. 3I Atlas is vaporizing nickel without iron. That's like finding smoke without fire, or shadows without light. It violates the basic chemistry of how these materials behave. Rahatgaonkar and Seligman propose a theory. Maybe the nickel is locked in some exotic molecules that break apart easily under ultraviolet light, releasing the metal at low temperatures. It's a reasonable hypothesis. The only problem is we've never seen these molecules. We don't know what they are. We don't know where they come from. It's an answer that creates more questions. But let's say they're right. Let's say 3I Atlas contains some unusual nickel-bearing compounds. That's interesting, sure, but it's not alarming. Then James Webb Space Telescope takes a look, and everything gets more complicated. The James Webb Space Telescope doesn't just look at objects, it dissects them. Its infrared instruments can identify individual molecules in a comet's atmosphere from hundreds of millions of kilometers away. When it turned its attention to 3I Atlas, scientists expected to see the usual comet chemistry. Lots of water ice, some carbon dioxide, maybe traces of methane and ammonia. The standard interstellar ice cream recipe. What they found was backwards. The coma, the cloud of gas surrounding the nucleus, contains significantly more carbon dioxide than water. Not slightly more, significantly more. In normal solar system comets, water dominates by a huge margin. It's like 80–90% water ice, with everything else being trace ingredients. 3I Atlas flipped the script. It's a carbon dioxide comet that happens to contain some water. Think about what that means for where this thing came from. Comets are frozen time capsules. Their composition tells the story of the stellar nursery where they formed. Water-rich comets like ours formed in regions where water ice could condense, where temperatures were in that Goldilocks zone. Carbon dioxide needs colder conditions to freeze solid, much colder. The researchers, Rahatgaonkar and Seligman again, conclude that 3I Atlas likely formed billions of years ago in an extremely cold region around another star, possibly in conditions colder than anything in our outer solar system. They suggest it might even predate our sun. Stop and consider that. This object could be older than our entire solar system. It could have been wandering through interstellar space when Earth was still a disk of dust around a newborn star. But here's what they don't say in the papers. What you have to read between the lines. If it formed in such an extremely cold environment, if it's been in the deep freeze of interstellar space for billions of years, why is it so active now? Remember, this thing was spewing water at 3 AU from the sun. It's releasing nickel vapor at 4 AU. Most comets don't even wake up until they're inside 2 AU. This ancient, deep frozen visitor should be the last comet we'd expect to see doing anything unusual. It should be dormant, inert, barely reacting to the sun's heat. Instead, it's the most active interstellar object we've ever observed. And then, there's the tail situation. September 2025. Nordic Optical Telescope in the Canary Islands captures something that makes absolutely no sense. The comet has developed an anti-tail, Not a regular tail that streams away from the sun like it's supposed to, but a spike of material pointing directly toward the sun. Now, anti-tails aren't completely unknown. Sometimes, when Earth passes through a comet's orbital plane, we can see dust particles that were ejected earlier, creating an optical illusion of a tail pointing the wrong way. It's all about viewing angle. Perfectly normal, perfectly explainable. Except 3I Atlas's anti-tail doesn't behave like an optical illusion. It appears, it strengthens, and then it rotates. By late September, telescopes observe it transforming into a regular tail, streaming away from the sun as expected. Dr. Avi Loeb from Harvard, who has become something of a lightning rod in the astronomy community, publishes his analysis. He doesn't mince words. The behavior, he suggests, resembles controlled maneuvering. Now, before you dismiss this as fringe science, understand who Avi Loeb is. He's not some UFO enthusiast with a blog. He's the former chair of Harvard's astronomy department, the founding director of the Black Hole Initiative, author of hundreds of peer-reviewed papers. When he talks, people listen, even when they disagree. His argument goes like this. The anti-tail appeared, strengthened, and rotated in a pattern inconsistent with simple outgassing and rotation. If the comet were just spinning and releasing gas jets randomly, you'd expect chaotic, unpredictable behavior. Instead, the transitions appear almost deliberate. He doesn't say it's definitely a spacecraft. He says we should consider it as one possibility among several. He proposes two scenarios. Either its intentions are benign or they're not. And he suggests we should probably figure out which one before it gets any closer to our planetary neighborhood. Most astronomers push back hard. They explain the anti-tail as a natural result of the comet's rotation and the geometry of dust particle ejection. They're probably right. Occam's razor says, given a choice between unusual comet behavior and alien spacecraft, go with the comet. But here's the thing. Even the skeptics struggle to explain all of 3I Atlas's behaviors with conventional comet physics. The nickel without iron, the inverted water CO2 ratio, the extreme activity at large distances, the geometric perfection of its trajectory. Each anomaly individually? Sure, you can handwave an explanation. All of them together in one object. That's when scientists start quietly admitting they don't have all the answers. And we haven't even talked about what happened when it swung past Jupiter. Actually, let me correct that. What's going to happen when it swings past Jupiter? Because that encounter is still ahead of us, and some researchers are watching those predictions very carefully. 3I Atlas's trajectory, mapped out with extraordinary precision by multiple observatories, will bring it uncomfortably close to Jupiter, then Venus, then Mars, which we already discussed, and then it leaves. The trajectory isn't random. It's almost a perfect grand tour of the inner solar system's major gravitational anchors. If you were designing a probe to study our solar system, to sample the gravitational fields of our major planets, to gather data on our sun's stellar environment, you'd plot a course remarkably similar to what 3I Atlas is following. Is that evidence of design? No. Interstellar objects can be captured into all sorts of orbital configurations by the complex gravitational ballet of the solar system. It's not impossible. It's not even improbable. But it is convenient. Let me shift gears and talk about something that doesn't get enough attention. What 3I Atlas is teaching us about planetary defense. The International Asteroid Warning Network, a global coalition that tracks potentially hazardous objects, has launched what they're calling the Comet campaign. From November 27th, 2025, through January 27th, 2026, they're conducting an intensive observation program not to study the comet's composition or origin, but to refine our ability to track it. Here's why that matters. When we talk about planetary defense, about protecting Earth from asteroid impacts, the critical first step is knowing exactly where the threat is and where it's going. With asteroids, That's relatively straightforward. They're solid chunks of rock or metal. You can pinpoint their center of mass, calculate their orbit, predict their position years in advance. Comets are nightmares for tracking. They have tails that obscure the nucleus. They have comas that make brightness measurements unreliable. They outgas unpredictably, creating tiny thrust forces that nudge them off their predicted trajectories. And if a comet is ever on a collision course with Earth, we'll need to track it with extreme precision to plan any deflection mission. 3I Atlas, with its prominent tail and active coma, is the perfect test case. It's close enough to track with ground-based telescopes, far enough away to be completely safe, and weird enough to challenge our observation techniques. The IAWN campaign is specifically focused on improving astrometry, the science of measuring celestial positions and movements. They're holding workshops, comparing techniques, calibrating instruments across dozens of observatories worldwide. They're treating 3I Atlas like a practice run for the real thing. Because, make no mistake, the real thing is coming. It's not if, it's when. Earth gets hit by small asteroids all the time. The big ones, the civilization enders, are rare but inevitable on geological timescales. And if one of those happens to be a comet, not an asteroid, we need to know we can track it. 3I Atlas might actually help save the world someday. Just not in the way you'd expect. Not through any properties of the comet itself, but by teaching us how to see clearly when our vision is obscured by gas and dust and uncertainty. They're even asking citizen scientists to help. If you have access to a decent telescope, they want your observations. Registration closes November 7th. This is one of those rare moments where amateur astronomers can contribute to genuine planetary defense research. But let's get back to the central mystery, because we've danced around it long enough. What is 3I Atlas really? Here's what we know for certain. 3I Atlas is between 2 and 6 kilometers across. That's a span that reflects our uncertainty, not the object's variability. We can't pin down its exact size because it's surrounded by that glowing coma, making precise measurements difficult. But for reference, we're talking about something comparable to a small mountain range, compressed into a single object, traveling at speeds that would cross the United States in about 90 seconds. Its mass, approximately 30 billion tons. To put that in perspective, that's about the weight of all the crude oil consumed on Earth in an entire year, compressed into a chunk of ice and rock. Or if you prefer a more visceral comparison, it's roughly equivalent to 150 of the largest oil tankers ever built, stacked together and frozen solid. Its velocity, 210,000 kilometers per hour relative to the sun. At that speed, it's one of the fastest moving objects we've ever tracked in our solar system. Only highly eccentric comets on kamikaze dives toward the sun move faster, and they're not sticking around for a tour. Its composition. Here's where things get complicated. The JWST data shows carbon dioxide as the dominant volatile, with water ice present but secondary. Carbon monoxide gas is also detected, suggesting extremely pristine, primitive ices. These are materials that haven't been processed by heat or radiation since they first condensed billions of years ago. Think about that preservation. This comet has been in cold storage at near absolute zero temperatures for potentially longer than Earth has existed. Every molecule in its ice is a fossil from another stellar system, another epoch of the galaxy's history, and now it's melting. Late August 2025, Gemini South Telescope in Chile captures detailed images of the coma and tail. The photographs show 3I Atlas surrounded by a glowing haze, classic signs of sublimation, ice turning directly to gas without passing through a liquid phase. The tail is growing, fed by streams of material ejected from the nucleus. By mid-August, when the Very Large Telescope detected cyanogen gas at 3 astronomical units, scientists realized this wasn't going to be a quiet passage. Cyanogen, a compound of carbon and nitrogen, typically shows up when comets get within about 2 AU of the Sun. 3i Atlas was releasing it at nearly double that distance. The pattern continues. Every observation reveals activity starting earlier and stronger than predicted. It's like the comet is more responsive to solar heating than it should be, more volatile, more energetic. Some researchers have speculated that the exotic composition, particularly the CO2-rich mixture, might lower the effective temperature needed for outgassing. Carbon dioxide sublimes at lower temperatures than water ice. Maybe that explains the early activity. But it doesn't explain the nickel. Let's revisit that anomaly, because it's the one that genuinely has scientists scratching their heads. Nickel vapor at 4 AU from the Sun, with no corresponding iron signature. The proposed explanation, exotic molecular compounds that photodissociate under UV light, is plausible in theory. In practice, nobody can point to a known compound that fits the behavior. There's another possibility that doesn't get discussed much in the papers, probably because it sounds too speculative. What if the nickel isn't coming from the ice? What if it's coming from the nucleus itself? Comets are typically described as dirty snowballs. Ice mixed with dust and organic compounds. But we've learned from missions like Rosetta that comet nuclei can be remarkably varied. Some have layered structures. Some have pockets of different materials. Some have regions that are more rock than ice. If 3i Atlas's nucleus contains exposed metallic materials, perhaps from a collision in its distant past, solar heating could be vaporizing surface metals directly. That might explain the nickel without iron pattern if the nucleus happens to have nickel-rich and iron-poor regions exposed. It's a stretch, but it's less of a stretch than invisible molecules we've never detected before. Now about that solar plasma impact on October 27th. Let's talk about what really happened and why the Russian astronomers' report is both reassuring and deeply strange. Coronal mass ejections are among the most violent events in the solar system. The Sun, in its ongoing nuclear fury, occasionally ejects massive bubbles of plasma. Billion-ton clouds of charged particles traveling at speeds up to 3,000 kilometers per second. When these hit planetary magnetospheres, they create auroras. When they hit satellites, they can destroy electronics. When they hit comets, they usually disrupt or destroy them. 3i Atlas took a direct hit from one of the largest CMEs of the current solar cycle. The timing was almost surgical, the CME arriving just as the comet reached perihelion, its closest and most vulnerable point. The Russian team's report said the signal was exceptionally weak after the impact, but the object remained on trajectory. Let's unpack that. The signal being weak could mean several things. It could mean the coma was temporarily disrupted, reducing the amount of light-scattering material around the nucleus. It could mean the comet was obscured by the plasma cloud itself. Or it could mean something else happened that we don't have the data to understand yet. But here's the key point. The trajectory didn't change. Not even slightly. The comet emerged from that plasma storm on exactly the path predicted before the impact. For a 30 billion ton object moving at 210,000 km/h, that requires remarkable structural integrity. Most comets that encounter strong solar activity show some response. They might fragment, releasing mini comets. They might experience increased outgassing on the sun-facing side, creating an asymmetric thrust that alters their orbit slightly. They might develop new jets or change their rotation rate. 3i Atlas did none of these things. It absorbed a hit that would vaporize a spacecraft, shrugged it off, and continued on its predetermined course like nothing happened. That's either a testament to its structural strength, or it suggests the nucleus is more cohesive, more solid than typical comets. Maybe both. The Russian team noted they'll continue observations as the comet emerges from behind the Sun in early November. That's the next critical window. If the plasma impact caused any delayed effects, any structural damage that's propagating through the nucleus, we'll see evidence in the coming weeks. The outgassing might increase dramatically if new surface area was exposed. The rotation rate might have changed if material was ejected asymmetrically. The coma might look different if the surface composition was altered. Or everything might look exactly the same, which would be its own kind of answer. Early November is also when the high-rise images from the Mars encounter might finally be released, government shutdown permitting. Those photographs, taken from just 12 miles away, could be the most detailed views of an interstellar object we'll get for decades, maybe longer. Think about what 12 miles means in astronomical terms. That's not a flyby. That's practically a rendezvous. At that range, high-rise should be able to see features as small as a meter across. We should see craters, if there are any. We should see jet sources, the specific vents where gas is escaping. We should see color variations, texture changes, maybe even the layering in exposed cliffs or fractures. The researchers said the images could reveal new details about the comet's jets and surface. That phrasing, again, is telling. They've seen the images. They know what's in them. And they chose the word could, not will or might. Could. As in, there's information there that could reveal something significant, but they're not ready to say what. Speculation time. What if the images show something unexpected? Not alien technology, but something that doesn't fit our comet models? What if the surface looks too young, or too old, or has features that suggest an internal structure we didn't anticipate? We won't know until we see them. And that waiting, that gap between what's known and what's knowable, is where the mystery lives. Here's another piece of the puzzle that deserves attention. 3I Atlas's discovery itself. July 1st, 2025. The asteroid terrestrial impact. Last alert system, ATLAS, picks up a new object. ATLAS is a network of telescopes specifically designed to detect asteroids that might threaten Earth. It scans the sky repeatedly, looking for anything that moves against the background stars. Most discoveries are routine. Near-Earth asteroids, main belt asteroids, occasional comets. The system catalogs them, calculates preliminary orbits, moves on. But when the orbit calculations came back for this object, someone noticed something unusual. The trajectory wasn't elliptical, it was hyperbolic. That's the mathematical signature of an object that's not bound to the sun's gravity. An object that's passing through, not orbiting. Hyperbolic orbits are rare, but not unheard of. Some long-period comets have orbits so stretched out they appear hyperbolic in the inner solar system. But when researchers ran the numbers backward, trying to figure out where this thing came from, they couldn't trace it to the Oort cloud, or the Kuiper belt, or any known reservoir of solar system comets. It came from outside, from the space between stars. Only the third time we've confirmed such an object, and by far the largest and most active. The first interstellar visitor, Oumuamua, passed through in 2017, cigar-shaped or pancake-shaped depending on who you ask, tumbling chaotically, showing no signs of outgassing but accelerating anyway. It sparked years of debate and speculation that still hasn't settled. The second, 2I Borisov, arrived in 2019. That one looked and acted like a comet. Water vapor, dust tail, typical spectroscopic signatures. Boring, in the best possible way. It proved that most interstellar objects are probably just comets and asteroids ejected from other star systems. 3I Atlas is somewhere between those extremes. It has a coma and tail like Borisov, but it has chemical oddities and behavioral quirks that echo Oumuamua's mysteries. What does that tell us? Maybe nothing. Maybe we've just been lucky enough to catch 3 very different types of interstellar objects in less than a decade. Or maybe there's a wider variety of objects wandering between the stars than we realized, each one carrying secrets from stellar systems we'll never visit. Let's talk about probability for a moment, because the numbers are more interesting than they first appear. 3 confirmed interstellar objects in 8 years. That sounds rare, and it is. But here's the thing. We've only had the technology to detect these objects for about a decade. Before 2013, Before the modern generation of survey telescopes came online, we were essentially blind to anything smaller than a planet passing through the outer solar system. The Pan-STARRS survey in Hawaii, the Atlas Network, the Catalina Sky Survey. These systems scan vast swaths of sky every night, building up a time-lapse movie of everything that moves. They've revolutionized our ability to spot faint, fast-moving objects, and immediately we started finding interstellar visitors. That suggests they're not rare at all. They're common. We just couldn't see them before. Current estimates, based on the detection rate, suggest that at any given moment, there might be dozens of interstellar objects passing through the inner solar system. Most are too small or too dark to detect. Some are moving through regions of sky we haven't surveyed yet. A few, like 3I Atlas, are large and active enough to announce their presence. Think about the implications. The galaxy is filled with debris, billions upon billions of comets and asteroids ejected from their home systems by gravitational interactions. Planetary formation is messy. When giant planets form and migrate, they fling smaller objects into interstellar space like cosmic billiard balls. Our solar system did this. We ejected countless objects into the galaxy during Jupiter and Saturn's early dance. Every star system with planets probably does the same thing. The result is a galaxy full of wanderers, homeless rocks, and ice balls drifting between stars. Most will drift forever, never encountering another star system. But some, by pure chance, will pass close enough to another sun to feel its gravity, to be warmed by its light, to briefly wake from their frozen slumber. 3I Atlas is one of those objects. It spent billions of years in the darkness between stars, a frozen time capsule from whatever stellar nursery birthed it. Then, entirely by accident, its trajectory intersected with ours. The odds of that intersection are astronomical, pun intended. The distances between stars are so vast that the chances of any particular interstellar object hitting any particular star system are vanishingly small. But multiply those tiny odds by the sheer number of objects out there, by the billions of years they have to wander, and suddenly it becomes not just possible, but inevitable. We're not special because 3I Atlas came here. We're special because we happened to be watching when it arrived. Now what happens next? The comet is currently behind the sun from Earth's perspective, making observations difficult. But in early November, it emerges. The first week of November is when ground-based telescopes will get their next clear look, when we'll see what, if anything, the solar plasma impact changed. Astronomers are preparing observation campaigns at observatories worldwide. The focus will be on several key questions. First, did the structural integrity hold? Are we still looking at a single coherent nucleus, or did the impact cause fragmentation? Even small cracks could propagate over time, potentially breaking the comet into pieces. Second, has the outgassing pattern changed? The jets, the specific locations where gas and dust escape the nucleus, are like fingerprints. If they've shifted, or intensified, or disappeared, that tells us something about how the surface was altered. Third, what's the rotation rate? Comets can spin up or spin down depending on how asymmetrically they release gas. If 3I Atlas's rotation changed, it suggests the plasma impact affected the surface distribution of active areas. Fourth, and perhaps most important, how bright is it? The brightness will tell us how much material is in the coma, which correlates to activity level. A dimmer comet might mean the surface was sealed, maybe by melted material that refroze. A brighter comet could indicate new vents opened up. The observations will continue through November and December as 3I Atlas gradually moves away from the sun. By late December, it'll be too far and too faint for most ground-based telescopes, though Hubble and JWST might still track it. Then comes the IAWN Comet campaign, starting November 27th. This is where the global coordination kicks in. Observatories across every continent, professional and amateur alike, all targeting the same object with the same goal. Track it with unprecedented precision. They'll measure positions down to fractions of an arcsecond. They'll compare techniques, cross-calibrate measurements, build the most accurate orbital solution ever computed for an interstellar object. And in doing so, they'll develop the protocols we'll need if we ever face a genuine comet threat. Because here's something that doesn't get emphasized enough. Comets are potentially more dangerous than asteroids. An asteroid is predictable. Its orbit is stable. If you calculate an impact trajectory, you can trust that calculation years in advance. A comet is chaotic. Every time it releases gas, it pushes itself slightly off course. The closer it gets to the sun, the more active it becomes, the more unpredictable its path. If a comet were on a collision course with Earth, we'd need to track it constantly, updating our predictions every few hours as new outgassing events nudged it around. 3I Atlas, with its strong activity and complex behavior, is teaching us how to do that. It's a drill, a training exercise for a threat we hope never materializes, but know is out there somewhere. By late January 2026, the campaign will conclude. 3I Atlas will be heading back out into deep space, moving toward the outer solar system and eventually beyond. By early 2026, it'll cross Jupiter's orbit outbound. By mid-2026, it'll pass Saturn's distance. By 2027, it'll be in the realm of Uranus and Neptune. And then, silence. It'll fade from view, becoming too distant and dim to track. Within a few years, it'll leave the solar system entirely, returning to interstellar space. But this time, it'll be different. This time, it won't be pristine. It'll carry traces of our sun's radiation, particles of the solar wind embedded in its ice, molecules altered by solar heat. In some infinitesimal way, 3I Atlas will be changed by its passage through our system. Billions of years from now, if it ever encounters another star, if there are astronomers there to study it, they might detect those traces. They might realize this comet visited another stellar system long ago. They might wonder what that system was like, whether it had planets, whether those planets had life, whether anyone there noticed when 3I Atlas passed through. The answer is yes. We noticed. We watched. We learned. But there are deeper questions we haven't fully addressed yet. Questions that orbit around the central mystery, like moths around a flame. Why is 3I Atlas so active compared to other interstellar objects? Why the chemical oddities? Why the structural strength that allowed it to survive the plasma impact without flinching? One school of thought suggests composition. Maybe its CO2-rich mixture, combined with whatever exotic compounds are producing that nickel vapor, creates a kind of super volatile cocktail. Maybe it's genuinely more reactive to solar radiation than water-based comets. Another school suggests age and processing. If this comet is truly ancient, if it formed in the very early days of another star system, it might contain materials we don't see in younger comets. Pristine, unprocessed ices from the primordial molecular cloud. Dust grains that predate the stars themselves. There's evidence for both views. The JWST composition data supports the exotic chemistry angle. The structural integrity suggests something dense and cohesive, possibly ancient and compressed. But there's a third possibility that I've danced around, but need to address directly. What if 3I Atlas is exactly what it appears to be? A comet, but from a stellar system so different from ours that its normal behavior looks anomalous to us. Consider, we've studied comets from one star system, ours. We've built our models on that sample size of one. We assume other stars produce similar comets, because why wouldn't they? Same physics, same chemistry, same basic building blocks of carbon, oxygen, nitrogen, metals. But stellar systems vary enormously. Different metallicities, different radiation environments, different planetary configurations. A comet forming in the disk of a metal-rich star might incorporate more heavy elements. A comet forming in the outer regions of a star with a strong stellar wind might have its surface processed in ways our comets never experienced. 3I Atlas might be perfectly normal for where it came from. It's just that where it came from had different rules than our cosmic neighborhood. That's simultaneously the most boring and most exciting explanation. Boring because it means no aliens, no exotic physics, just regular comet behavior from a different environment. Exciting because it means every interstellar visitor is a window into stellar systems we'll never otherwise study, each one carrying evidence of conditions light years away. If that's true, if interstellar objects are our only way to sample other star systems directly, then every single one we find is precious. They're not just curiosities or planetary defense exercises. They're ambassadors from distant worlds, messengers carrying information about the galaxy's diversity, and we've barely begun to learn their language. There's something profound about studying an object from another star system. It forces us to confront how limited our perspective really is. Every telescope we've ever built points outward from one planet, orbiting one star, in one corner of one galaxy. Every piece of astronomical data we've collected comes filtered through that singular vantage point. We're like someone trying to understand the ocean by staring at a single drop of water. Interstellar objects change that equation. They bring the ocean to us. 3I Atlas spent billions of years somewhere else. It formed in conditions we can only infer from distant spectroscopy. It was shaped by a star we'll likely never identify, in a planetary system we'll never observe directly. And now it's here, close enough to study in detail, carrying physical samples of that alien environment. Think about what the JWST data represents. Those aren't just measurements of carbon dioxide and water ratios. That's a chemical fingerprint of another star's planetary disk. The temperatures, pressures, radiation levels, even the timing of planetary formation. All of that information is encoded in the ice currently sublimating off 3I Atlas's surface. We're watching billions of years of history evaporate in real time. The nickel emission, weird as it is, tells us something about the mineral content of that distant system. The CO2 dominance tells us about temperature gradients in the protoplanetary disk. The carbon monoxide suggests the comet formed far from its parent star, in the coldest reaches of that system. Each data point is a piece of a puzzle we're only beginning to assemble. What kind of star system produces comets like 3I Atlas? Was it a system with massive gas giants that scattered material into interstellar space? Was it a system that experienced some catastrophic event, ejecting its outer regions wholesale? We don't know, but we're learning to ask better questions. And here's where things get interesting from an astrobiology perspective. If comets from other star systems can reach us, then comets from our system can reach them. Material exchange between stellar systems isn't just possible, it's inevitable. Comets aren't just ice and rock. They contain organic molecules, the chemical building blocks of life. Every comet we've studied in detail has shown complex carbon chemistry, amino acid precursors, sometimes even amino acids themselves. They're like chemical factories, mixing and processing materials in ways that might seed the conditions for life. If our solar system has been receiving interstellar comets for billions of years, and we're only now detecting them because our technology improved, that means Earth has been receiving deliveries from other star systems throughout its entire history. Did any of those ancient impacts contribute to Earth's organic inventory? Did they deliver molecules that became part of the prebiotic chemistry that led to life? We can't know for certain, but the possibility is tantalizing. Flip that around. Our comets are reaching other star systems. Right now, somewhere in the galaxy, there might be a comet from our Oort cloud approaching another star. Maybe it'll pass near a planet. Maybe it'll impact that planet. Maybe it'll deliver organic molecules from Earth's neighborhood to soil light years away. We're not isolated. We're part of a galactic network of material exchange that's been operating since stars first formed. 3i Atlas is just one node in that network, one packet of data in a cosmic internet that predates civilization by eons. But let's bring this back to the immediate mystery. What does 3i Atlas tell us about the search for intelligence? Avi Loeb's hypothesis about controlled maneuvering, controversial as it is, forces us to think about what evidence of technology would actually look like. If an advanced civilization wanted to explore the galaxy, sending crewed starships is absurdly expensive and slow. But sending probes, small automated spacecraft that coast between stars using minimal energy, that's potentially feasible. A probe wouldn't need life support or massive fuel reserves. It could be compact, durable, designed to survive millions of years in interstellar space. And if you wanted that probe to visit multiple star systems efficiently, you'd give it some ability to adjust its trajectory using local resources. Comets naturally outgas, releasing jets of material that act like tiny thrusters. If you were designing a stealthy probe, disguising it as a comet, and using controlled outgassing for maneuvering would be brilliant. You'd be practically invisible, indistinguishable from natural objects unless someone looked very carefully. Is that what 3i Atlas is? Almost certainly not. The evidence for it being a natural comet is strong, and the anomalies, while interesting, aren't inexplicable. But the fact that we can't immediately rule it out, that's significant. It means our ability to distinguish between natural and artificial objects at interstellar distances is still developing. It means we need better criteria, sharper observations, more sophisticated analysis. The next interstellar object we detect might be artificial, or the one after that, or the 100th one. And when we finally encounter actual alien technology, we need to recognize it for what it is. 3i Atlas is practice. It's teaching us what questions to ask, what measurements to take, what anomalies matter, and which ones are just noise. The fact that serious scientists are even having this conversation, that papers are being published debating the possibility, that's progress. 20 years ago, suggesting an interstellar object might be artificial would have been career suicide. Today, it's speculative but acceptable, as long as you acknowledge it's a low probability hypothesis. We're learning to think about these possibilities rigorously, without dismissing them out of hand, and without accepting them uncritically. That's the scientific method working exactly as intended. Now, what about the future? Where does interstellar object research go from here? The Vera C. Rubin Observatory, currently under construction in Chile, will begin operations in 2025. It's designed to survey the entire visible sky every few nights, creating an unprecedented catalog of moving objects. Current estimates suggest it might detect 1 or 2 interstellar objects per year once fully operational. That's a revolution. Instead of 3 objects in 8 years, we could be looking at dozens over the next decade. Each one a new data point, a new chemical fingerprint, a new piece of the galactic puzzle. NASA has proposed missions to rendezvous with interstellar objects, to actually send spacecraft to intercept them while they're still in our solar system. The technical challenges are immense. The objects move fast, and we typically don't spot them until they're already close, leaving little time to plan and launch a mission. But it's not impossible. With enough advance warning, with a spacecraft already built and waiting, we could do it. We could send a probe to fly alongside an interstellar visitor, to sample its coma, to photograph its nucleus from meters away, maybe even to land on its surface. Imagine the data from a mission like that. Direct sampling of material from another star system. Chemical analysis with laboratory precision instead of remote spectroscopy. Close-up imaging that reveals texture, structure, composition in exquisite detail. That's the dream, and it's closer to reality than most people realize. ESA has discussed similar concepts. China has included interstellar object intercept missions in their long-term space strategy. Russia has proposed using high-speed spacecraft, possibly nuclear-powered, to chase down fast-moving visitors. The race is on, not between nations, but between humanity and opportunity. These objects don't wait. They pass through our neighborhood briefly, and then they're gone, often before we've even identified what they are. 3i Atlas is a perfect example. We found it in July. By January, it'll be leaving. That's 6 months, from discovery to departure. Not much time to organize a mission, even if the spacecraft already existed. But the next one, maybe we'll be ready. Maybe we'll have the technology positioned, the plans made, the funding allocated. Maybe we'll actually catch one. And when we do, when we finally get close-up data from an interstellar object, we'll answer questions we haven't even thought to ask yet. For now, 3i Atlas remains at a distance, observable, but untouchable. The best we can do is watch, measure, analyze, and learn. And honestly, that's not nothing. Every data point we collect contributes to a larger picture. Every observation refines our models. Every anomaly we investigate teaches us something about the limits of our knowledge. The fact that we're having trouble explaining all of 3i Atlas's behaviors isn't a failure. It's an opportunity. It means there's something new to learn, some aspect of comet physics, or interstellar chemistry, or stellar system formation that we haven't fully grasped yet. Science advances by finding things that don't fit, that break our models, that force us to think differently. 3i Atlas is doing exactly that. So here we are, at the end of October 2025, watching an ancient visitor from another star system as it rounds our sun and prepares to leave. What have we learned? We've learned that interstellar space isn't empty. It's filled with wanderers, objects ejected from their home systems billions of years ago, drifting through the darkness until, by pure chance, they encounter another star. We've learned that these visitors arrive more frequently than we thought, and we've only just developed the eyes to see them. We've learned that every star system is unique, producing comets with compositions and behaviors that reflect their local conditions. What's normal in one stellar neighborhood might be bizarre in another. 3i Atlas's chemical oddities might not be anomalies at all, just the signature of a different kind of stellar nursery. We've learned that our models are incomplete. The nickel emission, the inverted ice ratios, the extreme early activity. These observations are pushing the boundaries of what we understand about comets. That's uncomfortable for scientists who like their theories neat and tidy, but it's also exciting, because it means the universe still has surprises left. We've learned that survival in space requires remarkable resilience. 3i Atlas took a direct hit from a plasma storm that would destroy most human spacecraft, and it didn't even slow down. Whatever this thing is made of, however it's structured internally, it's built to last. That structural integrity, maintained across billions of years of interstellar travel and now tested by our sun's fury, tells us something about the durability of natural objects in the cosmos. And perhaps, most importantly, we've learned to ask better questions. Is it a comet? Almost certainly yes. Is it a normal comet? That depends on what normal means when you're talking about objects from other star systems. Is it alien technology? Probably not, but we can't completely rule it out with current data, and that gap in our certainty is itself valuable information. The November observations will be critical. When 3i Atlas emerges from behind the sun in early November, astronomers will be watching for any changes. Did the solar plasma impact alter its structure? Did new vents open up? Did the rotation change? The answers will tell us whether our understanding of comet resilience needs updating. And those high-rise images, if they're ever released, could rewrite what we know about interstellar object surfaces. 12 miles is close enough to see details that might resolve some of the mysteries, or create entirely new ones. But even if we never get those images, Even if 3i Atlas keeps some of its secrets, we've gained something invaluable: perspective. For most of human history, we thought comets were omens, supernatural signs from the gods. Then we learned they were natural objects, following predictable orbits made of mundane materials. That understanding stripped away the mystery, but gave us knowledge. Now we're learning that some comets aren't from here at all. They're visitors from other stellar systems, carrying information about places we'll never reach, formed under conditions we can only infer. That gives us back some of the wonder, but this time grounded in scientific observation rather than superstition. 3i Atlas is a messenger, whether it knows it or not. It's telling us that the galaxy is more connected than we realized, that material flows between star systems, that the universe is constantly shuffling and redistributing the building blocks of planets and possibly life. It's telling us that we need better detection systems, better tracking methods, better theories. The Vera Rubin Observatory, the IAWN campaigns, the proposed intercept missions, these are all responses to the realization that interstellar objects matter. They're not just cosmic curiosities. They're data sources, teachers, maybe even threats we need to learn how to handle. And on a deeper level, 3i Atlas is forcing us to confront our assumptions. When we see something behaving strangely, our first instinct is to fit it into existing models, to find the explanation that requires the least revision of what we already believe. That's usually the right approach. But sometimes, the strange behavior is trying to tell us that our models are wrong, that we've missed something fundamental. The question is, how do we know which is which? How do we distinguish between an anomaly that's just a measurement error or an unusual combination of known factors, and an anomaly that's pointing toward new physics, new chemistry, maybe even new categories of objects? We don't have a perfect answer to that. We navigate by feel, by experience, by the collective judgment of the scientific community. Sometimes we get it wrong. Sometimes we dismiss things we should pay attention to, or pay attention to things that turn out to be noise. But the process works, slowly, incrementally, over years and decades. The truth has a way of surfacing eventually, as long as we keep looking, keep measuring, keep questioning. 3i Atlas will leave our solar system in the coming months. By this time next year, it'll be too faint to observe from Earth. Within a few years, it'll be beyond even our most powerful telescope's reach. But the data will remain. The spectroscopic signatures, the brightness curves, the trajectory measurements, all of it preserved in archives and databases. Future scientists, with better theories and better tools, will return to this data again and again, extracting new insights we missed. That's how science works. We build on what came before. Every observation becomes part of the permanent record, waiting to be reinterpreted, reanalyzed, understood in ways we can't anticipate. Maybe in 20 years, someone will look at the 3i Atlas data and have an epiphany that explains everything. Maybe they'll realize the nickel emission was a clue to some aspect of stellar metallicity we hadn't considered. Maybe they'll connect the CO2-rich composition to a particular type of protoplanetary disk. Maybe they'll figure out that the structural integrity tells us something important about how comets survive in interstellar space. Or maybe 3i Atlas will remain a mystery, one of those objects that doesn't quite fit, that keeps defying complete explanation. Either way, it's changed us. It's expanded our understanding of what's possible, what's out there, what we still have to learn. And it's reminded us that we're not alone in the universe, even if we haven't found life yet. We're connected to other star systems through these wandering ambassadors, these frozen time capsules that carry the chemical memory of distant stellar neighborhoods. Every few years, another one will arrive. Each will be different. Each will teach us something new. And slowly, observation by observation, we'll piece together a picture of the galaxy beyond our immediate neighborhood. That's the real value of 3i Atlas. Not whether it's a comet or something else, not whether it fits our current models, but what it represents, the beginning of a new era of astronomy. We're no longer limited to studying distant objects with light that's traveled for years or centuries. We can now study physical samples from other star systems, pieces of other stellar neighborhoods that have come to visit us. That's revolutionary. That changes everything. So watch the sky in November. If you have access to a telescope, join the observation campaign. If you don't, follow the reports from those who are watching. Because 3i Atlas is still out there, still moving, still carrying its secrets, and we're still learning. And when it finally fades from view, when it returns to the darkness between stars, it won't be the end. It'll just be the beginning of a wait for the next visitor, the next mystery, the next opportunity to learn something we didn't know before. The universe is vast and strange and full of wonders. 3i Atlas is just one of them, but it's ours to study for this brief moment in cosmic time, and we're not wasting the opportunity. That's what makes us human. We see something we don't understand, and instead of fear or indifference, we feel curiosity. We build telescopes, we develop theories, we ask questions and seek answers. 3i Atlas is moving away from us at 210,000 kilometers per hour, carrying the mysteries of another stellar system back into the void. But it's leaving something behind: knowledge, questions, and the certainty that we're part of something much larger than ourselves. And maybe, just maybe, that's the most important discovery of all.